pleased today to be able to present to you a demonstration of the 2015 improvements in integrating your geological and geophysical interpretations within a robust and performant geomodeling environment. Today's agenda. GeoGraphix 2015 brings an impressive list of significant enhancements to integrating geological and geophysical interpretations, including but not limited to graphical curve normalization for fast interactive curve normalization, improved integration between your geophysical and geological interpretations through the advanced velocity modeling, integrated seismic horizons and faults in the geomodel constraints, and dynamic depth-converted seismic backdrop in the smart section cross-sections. Our new quick pick mode for fast correlations. We also incorporate interval points from your SmartStrat geostring correlation into the size vision velocity model for more accurate velocity modeling and depth conversion. All this we can view within a dynamically and improved 3D advanced visualization environment. And lastly, I'll wrap up by answering any questions you may have and directing you to additional resources to further advance your understanding of the GeoGraphix offerings. We have focused on, in 2015, speed, accuracy, and enhanced decision making. Speed to reduce the cycle of prospecting through production through a direct and seamless integration between domains. In accuracy, we've increased the accuracy of reservoir interpretation through an extensive 3D geomodeling to bring all the domains together in time or depth. All this goes together to make better decision making, to see all the possibilities in one 3D scene to make the best economic decisions possible. On for the demonstration. Our workflow will be examining the Barnett geology and modeling it in 3D within Smart Section with the Frame Builder geomodeling engine running. Next, we'll normalize the curves with our new graphical curve normalization tool. We'll then pick our target surface and model that in 3D. Then we'll shift domains over to the geophysical domain and examine and interpret the Barnett 3D seismic survey. And then come back and do some geosteering and also updating the velocity modeling, incorporating interval points within the SmartStrat geosteering environment. And all integrated within our 3D geomodel, which we will then update and view in 3D. What you're seeing here is the map view of Smart Section. Smart Section is our 3D geomodeling environment that has both a map view and a cross-section view to interact with the 3D geomodel. Behind Smart Section, I have running Frame Builder. Frame Builder is our topology engine that allows us to load any surface from our active strat column and set up a hierarchy of surface constraints. For example, the basal Atoka here will control the conformance of a limestone and an M marker, and the upper Barnett surface here will be also constrained by the basal Atoka, but it in turn will constrain the Barnett maximum flooding surface, the basal Barnett, and the Ellenberger. So let's look at this cross-section here of the vertical wells. Currently, I've got 3 vertical wells. The surfaces are being modeled on the fly with triangulation and minimum curvature smoothing. Currently, each surface is being modeled independently. You can see this is a very naive interpretation. But because we have a conformance technology within Frame Builder, once I apply the conformance tool, you will see these surfaces will now conform to the hierarchy I set up based upon the basal Atoka. Also within the map, I'm currently showing the upper Barnett, but if I turn on the Ellenberger and toggle on and off the conformance, you'll see that the Ellenberger, being a deeper surface, is only picked in 3 surfaces. Therefore, it's only modeled over the convex hull of the data distribution. But once I turn on the conformance, again, it is modeled based upon the conformance of the basal Atoka on down. Now let's look at this first well in our cross-section here in Prism. So I'm going to shift over to Prism. We're looking at a model here of our mineralogy based upon a PEM, an external model that I've got running in the background. But before we can get good interpretations, we first have to normalize the input curves, particularly the gamma ray curves. So we have a new curve normalization tool where I will model or normalize the gamma ray for this well here. This will be our reference well. I'm going to go ahead and make that full screen so you can see it a little better. And then I'm going to set up the other two wells, which I've got in a filter. So these are the other two wells that I'm going to be normalizing. And it sets this up in a list. Now this list could be many wells, but in this case I'm just normalizing the other two within the cross section. We have the ability to do individual manual normalization or a batch process where we have three methods available: the average method, the single point method, and the 2-point method. We can also discriminate using any kind of log curve or any kind of interval to associate the normalization to the zone of interest. This manages just the statistics for the normalization process, but not the output. The output, the normalization, is applied to the entire well curve. But in this case, since I have so many fewer wells, I'm just going to use the manual method. So we'll click on the first one and look at the first one. I've got three vertical lines. The middle vertical line is representing the P50 statistic. And the first process is just simply to move this around. And I'll turn off the input curve so it's not to be too complicated here. Then we have a P minimum, which by default is set at the P5 statistic, and a P maximum, which by default is set at the 95 statistic. Those can easily be changed with a right click and move that to any maximum P value you want, or right click on the minimum and adjust that to any P minimum value you want to. And then with the left click, you can adjust those so the tails line up and the cumulative frequencies line up. Once this is done, you can see that the status is processed. I then click the Save button, and that is now output by default to a gamma ray underscore norm curve name. I can make that any curve name I want to, but that is just fine. Save that one. Go to the next one, and actually it looks pretty good. I don't even think I even have to do much. Maybe adjust the tails just a little bit, and then save that one. So that's now saved back to the representative curve sets. So these are now normalized. So any kind of petrophysical analysis I do, particularly that consumes the gamma ray curve, will be done on normalized curves. What we're looking at here is a mineral model. It's actually a 6-mineral model. 3 competent mineral models, or mineral components of sandstone, limestone, and dolomite are being shown. By the way, this dark green line here, that's the upper Barnett. The light green line here is the Barnett maximum flooding surface. The blue line here is the basal Barnett. And down here at the bottom, we have this magenta line here, which is the top of the Ellenberg, which is a Canberra Ordovician carbonate. So I'm analyzing for the competent components, sandstone, limestone, and dolomite, and you can see between the maximum flooding surface and the basal Barnett, I've got a buildup of the competent components. And additionally, I'm looking at 3 components of the clay minerals. This is particularly important when you're doing shales, because clays can have a very significant impact on how you drill and complete these wells. For example, I'm analyzing for kaolinite, illite, and chlorite. Kaolinite is fairly innocuous clay, and it's probably around a 20 to 30% component of the clays. Illite, I don't really have much illite in here to worry about. But I do have a fairly good cut of the chlorite. Chlorite is an iron-bearing clay, and if you acidize that, it liberates the silica into a gel-like substance, which will plug up any permeability or porosity you may have. I'm also analyzing for effective and average porosity, because a lot of the storage capacity is within the standard type of conventional porosity within these competent components. I'm also analyzing for TOC. And I've got 3 curves over here to look at an empirical indication of organic clay, or organic shale. So I'm crossing the curves for gamma ray versus rho v, gamma ray versus Vn, gamma ray versus deep resistivity. And I'm laying those curve scales one on top of the other in an area where I think it is inorganic clay or inorganic shale. Where these curves cross, that's an empirical indication of organic clay. So I think this is a pretty good target. So I want to make this my target zone right in here where I've got the most confident components. So now we're going to return back to our geomodel. I'm going to click on the tab, or the templates tab, and I'm going to apply my clay minerals and TOC templates so I can now not only look at the cross section, but I'm also going to be looking at the model that I'm running. So this right in here is going to be my target. So let's go ahead and make a new target. And I'm just going to call this my Barnett target. And I'm going to turn on the picking mode once that is set. Picking mode for the target. Let's do it right there. Right here, and right here. Now I'll turn off my picking tool so I don't inadvertently pick something I didn't mean to. Return to my map view. Turn on the Barnett target surface, and again, it's only modeling these 3 wells. But because I do have that topology engine behind me, if I come back in here and I put the Barnett target within its correct stratigraphic position within the hierarchy of the constraints, it will be modeled now in 3D over the area that I have actual control. Now this is all currently with well control. Well, fortunately, I have a 3D seismic volume over the area. This section here is the same log, same section I used when I analyzed the petrophysics. I've used log M to tie the geology to the geophysics with this synthetic seismogram. So I know that this is the M marker at the top, the LS limestone marker here, the basal Atoka, all the way down to the Ellenberger. Now I'm going to go ahead and pick the M marker, so I'm going to activate it and use my 2D auto picking for this and also on a regional line here. And return to the map for the M marker. I'm going to go ahead and correlation auto pick that. So now I've got 3 surfaces that are 3D auto-picked. I've got that M surface, which I just did, the limestone surface just below that, and then down here I've got the Atoka. So I've got 3 3D auto-picked surfaces. I'm going to use that to make a new velocity model. I'm going to correlate my time values for the M, LS, and Atoka time horizons and correlate them with their corresponding formation picks from well base for the M, LS, and basal Atoka. In addition, I'm going to incorporate interwell points for the Atoka. I'm going to be using this when I geosteer the well to use the interwell points from SmartStrat to update my velocity model. So let's go ahead and apply this model and pop this back so you can see everything pop into their corresponding event when I apply the velocity model. And now everything is snapping to its corresponding event. So a very robust 3D velocity model that's now available to me for me to use back in my geomodel. So I'm going to return to my correlation template. And I'm going to now incorporate a new feature for 2015. I've got a horizon here called the Atoka from SeisVision. Previously, we had data points we could use in the geomodel from well base or the data points off an isomap layer. We also had isomap grids we can incorporate, but now we can incorporate live depth-converted seismic horizons as sources for both our surfaces and faults coming directly from SeisVision and converted from time to depth with the velocity model. Now, in addition, I'm going to make my basal Atoka conformable to the Atoka from SeisVision. Click OK and rerun my model. And now you can see I've got a much more well-constrained and conformed model because I have information coming in the interwell area from the seismic surfaces. Additionally, if I return to the map you will see that let's return to well, the Barnett target's fine. We can actually color that if we'd like. Let's go ahead and turn on the colors. You can see it's much more high frequency information because we're incorporating interval data from the velocity model through the depth converted seismic surfaces. Now let's go ahead and bring up a section that we're actually drilling, and let's go ahead and put this at the bottom so we can see the rest of our grid. And open up this drilling vertical section, cross section. This is a well that's currently drilling. I'm looking at my 3D surfaces. This is the upper, or I should say basal Atoka, upper Barnett. This is my maximum flooding surface, which in this case was the target horizon. I got my basal Barnett and the Ellenberger down here at the bottom. I'm going to launch the Smart Strat mode. Smart Strat mode is an extension of the Smart Section cross section that allows us to do correlations and of the horizontal well so that we can correlate it within the geology and then use that information to geosteer the well. I'm going to make my active surface my upper Barnett surface and change the curve scale from 0 to 200 API units for the gamma ray. And I'll draw your attention to this vertical panel on the left. Currently, this is using a TVT correction, or a type log, TVT corrected for the local well here. I can use any offset type log, but if the geometries are correct, the closest vertical well to you is the actual well you're drilling right here by itself. The panel down here at the bottom, the horizontal panel, and I'll zoom in a little tighter, showing two curves. The red curve is the LWD curve. That's the same gamma ray curve you're seeing on the log on the cross section itself. The blue curve is what we call a predicted curve, and it's based upon the dip. So as I adjust dip, you'll see on the vertical panel to the left, I'm sampling a different part of the type log. And so I adjust that until I get the predicted curve to match the LWD in the near portion of the well, like I'm showing right here. And then I simply right-click and add a tie point, and that creates that first dip segment, indicating we have a dip of a little over ½ a degree. I can continue that process down the borehole by looking at the horizontal panel, lining things up, and another tie point there. Another way I like to do is I like to actually divide this up into segments. I look at patterns. If I have like a smile pattern here, a frown pattern here, those are potential stratigraphic traversals. So I like putting what I would call a trial tie point at one of those potential traversal points. Click right in here to this segment and draw your attention over to the vertical panel. And you can see that this blue section is the TVT conversion of the LWD in this little dip segment right here, and I just match it to the type log. I can continue on, double click, we'll also put a tie point there, click in that segment, and simply grab the TVT of the LWD and match it up, and just work on down the borehole. Like I say, at any point I could change over to an offset type log, but this actually works fairly well for our purposes. Maybe a couple more. Pull that down a little more, something about right. That, and then one more at the very end. Something about like that. So what I've got is a correlation of my dip segments represented by this magenta line. This is the active smart section or smart strat model from my 7 or 8 different dip segments. Now you'll notice that the upper Barnett here is the active surface for smart strat, but it's not matching the upper Barnett from our geomodel. So we need to update our geomodel based upon our horizontal correlation here. And to help us do that, I'm going to hang some type logs. These are the type logs I use for the correlation purposes. Can hang those right there. And this will help me put my inner wall points on here to tie the SmartStrat correlation to my geomodel. So returning to my Surfaces tab, and remember that, just to remind you, that the basal Atoka is controlling the upper Barnett, and the upper Barnett is controlling these other surfaces. So I'm going to put some interwall points for the basal Barnett. And I'm going to use a new mode called Quick Pick mode. I'm going to enable the Quick Pick mode. The Quick Pick mode suspends the geomodeling to allow you to make picks just as fast as you can click on your cross section. Go to the upper Barnett and do some quick picks there. You can also adjust these. There is a multi-level undo and a multi-level redo. So you can play around with your correlations until you're happy with them, and then you just commit them to the database and the geomodel all at once. So I'm going to save my quick picks and have it all modeled all at once on the fly. There. So everything is tying very nicely, and I've got that correlated. And I'm turn off my quick picks and my picker tool. Now let's turn on the seismic backdrop. Now notice, and I'll refer you back to the synthetic here, that the basal Barnett should be the strong positive reflector right here. Well, as I look on my SmartStrat cross-section, I know that it's not matching. That's because I haven't had the ability until now to incorporate interwall points that I've used to correlate the well bore along the horizontal reach of the well. So now I'm going to update the velocity model, which will take these interwall points, these will be the depth points, with their back interpolated horizon from size vision, which will make time depth pairs along the horizontal, update the velocity model, and now you see everything is snapping right to their corresponding event. So not only geosteered this well and correlated into the geology, I've updated my velocity model in size vision, so I've got the most accurate velocity possible, which then helps me build the most accurate geomodel possible, so the next well that I would plan would be into the most up-to-date and accurate geomodel possible. Go ahead and save this and close the cross section. Return to my map. Now in the background here, I've got my vertical wells, and if I turn on my seismic backdrop, you'll also see how well the Atoka events are now tying in to my geomodel. So this is the depth converted seismic backdrop based upon that updated velocity model. Zoom out here, and we're going to go ahead and look at this in 3D. So I've got, let me just bring my Barnett target down a little farther so you can see everything, see my culture and my wells. And I've got a 3D probe here. This is also new for 2015. We now have the ability to draw these probe areas and then open up our new advanced visualization environment just within the extents of this probe area. And we'll also load in any wells that are in the interpretation. Any cross-section, any well-to-well cross-section will become a vertical Spitz diagram in 3D, and also any of these surfaces will be available. So I'm going to right-click and display this in 3D, and this will launch our new Pro 3D Advanced Interpretation environment. And it will make a listing of different 3D objects over here on the left-hand side. So it's loading the wells with the log templates. Then it will proceed to load all the available surfaces. If I have any faults in here, so here come the formation tops are coming in, surfaces, faults. And I'm going to shift over here and use my cool little Xbox controller to come in here. Now you're looking at a couple of the surfaces. Let me open up the tree over here and let's see which surfaces we're looking at currently. We're looking at the Atoka from size vision, and we're looking at the Barnett target, which is fine. So let's go ahead and I'm going to just take the set of the Atoka from size vision. I'm just going to open up the basal Atoka just for now. Now the Spitz diagram is showing the lithology fill that's correlated to the surfaces or the formations in our strat column. Now I can also load in for this cross section. I'm going to load in log curves, the gamma ray. Remember we normalized the gamma ray for import 1 curve set, so go ahead and load those in. And I'm going now to shift from lithology fill mode over to color mode. And going along with my earth tones, I've got an earth tone 2 spectrum, but in order to really zero in on the interesting portions of it, I've got a new histogram control for my color control that I can now block in the amplitudes of my color spectrum that I think are the most interesting. And you can see now, as I zoom in and up and down, let's just pull that back up here, you can see where I'm showing non-shale, or it could be sand or limestone. I'm also have a corresponding spectrum color that's showing that. So I've interpolated a petrophysical attribute along the face of the fence diagram based upon the active log control. I'm also showing templates. These are the same templates that were used to build the cross section over in Smart Section, so you can compare your prism templates to your interpolated values. I can also click on the surface of the fence diagram, right-click, and display the seismic, and this will display the depth-converted seismic along here. And if I zoom in, and I'm going to turn off the correlation so you can see this a little better, and if I change the opacity of my fence diagram, I can start to co-blend back these petrophysical attributes against any kind of geophysical attributes. Now currently I'm showing an amplitude volume, but if you use the LMKR's volume attributes tool, you could put an attribute out of, say, curvature or similar to ESP or any other attribute and co-blend those back against each other to kind of interpolate or understand what you're seeing in your seismic section based upon your interpolated log values. Let's go ahead and put that back. I can also show any seismic slice. I'm going to show a seismic slice here, and I'm going to shift my view so I'm looking down on the slice, and I'm also going to change my template. Now this slice is actually built from LMKR volume attributes, and it's a semblant slice, which is best shown in a grayscale. So we'll change that to a grayscale. And as I move down through it, you can see some interesting anomalies. These are karsting figures resulting from the collapse within the karsting of the Ellenberger surface. Those constitute geohazards, and you want to be aware of those when you drill because there will be hazards that are wet conducting water up from the Ellenberger. So let's remove that and return to my other view. Oh, I should reverse my yoke. I used to fly small airplanes, and I prefer when I push things down, I go down, and when I pull things up, I go up. That's better. Yeah, that's better. I'll scoot down here, and I'm going to remove the seismic line for now, and I'm going to go ahead and go back and turn on my, see, my Ellenberger target. I can go back to Smart Section, and on my Ellenberger, on my Barnett target, I should say, if I make that the active surface, that should then come in here and put contours on my surface. Now also notice that I'm also following very nicely, there my contours showing up, very nicely the structure on my surface here with my fence diagram. Spin around here, you can see it much better on this side. You can see very nicely the structure indicated by the contours, and also the 3D view of my Barnett surface is following very nicely the corresponding events in the fence diagram. This new environment is very performant. It's built on Xbox gaming technology. We will be putting in some interpretation capability. Currently, you can actually show your tops here with indicated markers and move those if you need to correct them with some other seismic information. I can click on any well, and I can show and display any seismic depth converted. I can return this to a different spectrum. Here we are. And I can show that depth-converted seismic section right around the wellbore. This can be very useful once you're drilling a well. You can actually wrap that depth-converted seismic around it to get a feel for what's in front or around the wellbore that's not apparent from your well log data. So it's all very tightly integrated between the domains of geology, petrophysics, geophysics, GIS, and 3D visualization. This is what 2015 GeoGraphix brings to you. So as you can see, LMKR GeoGraphix 2015 brings to you an improved geological and geophysical interpretation integrated within a robust 3D geomodel. LMKR enhances the GeoGraphix workflow experience by improved integration between the disciplines of geology, geophysics, petrophysics, and geomodeling. All this capability enables the creation of a robust and sophisticated Earth model to help target the optimum zone to lower drilling risk and improve your return on investment.